Our study of correlation will involve hypothesis tests, much like the hypothesis tests of a previous chapter. So recall that we said the value of R, our correlation coefficient, the linear correlation coefficient, has values between -1 and 1 inclusive. There's -1, here's 1, and right in the middle is 0. And what we said before was that 0 represents no linear correlation. So for our hypothesis test, our null hypothesis will state that the population parameter for the linear correlation coefficient rho, recall that we use the parameters here in our hypothesis test, is 0. In other words, the null hypothesis will always be, this, that there is no linear correlation. So the alternate hypothesis then will say what? What's everything else? It is not 0. This is how they will always be stated. And as we did before, we'll find a critical value, a test statistic, a p-value. We'll make a decision. We'll have a decision diagram, and it will look like much like what I've drawn there, but I'm going to draw it again down here. So our decision diagram will be this number line between -1 and 1. We'll have 0, and then we'll have our critical values. It's a two-tailed test, right? So we'll have two critical values, the positive and negative of the same. We'll have a shaded region, our critical region here and here. And this is the number line for R. So then we'll have our test statistic. Recall that will be an R value, and our critical value will be an R, and we're comparing these two. We'll see if our test statistic falls in either one of these critical regions. If it does, we will reject the null hypothesis as we did before. And we'll talk about our how we make our decisions here in just a minute. So where will we get our critical value? The critical values are in the linear correlation table in the back of our textbook, and it's given for an alpha of 0.05, a significance level of 0.05, or for an alpha of 0.01, and then for certain n values between 4 and 100, certain selected ones. So we'll be using that table in the back of the book to find these critical values. The TI-8384 technology will give us the test statistic and the p-value, just like we had with our hypothesis test of the mean and of the proportion. And then we'll make our decision. The decision choices are the same. Reject the null hypothesis, reject HO, or fail to reject the null hypothesis. Fail to reject HO. So that hasn't changed at all. Okay? So if we let's look at the different decisions methods that we have. We have two, just as we did before. If the p-value is less than or equal to the significance level, which is alpha, this is what we'll conclude. There is sufficient evidence to support the claim of a linear correlation between x and y. And now we won't say x and y. X will be something like the sunlight exposure, amount of sunlight exposure, and y will be the height of the plant. So we'll use the actual language here for x and y, but this gives us a pattern of how we'll write our conclusion if our p-value is less than or equal to alpha. So why would we say there's evidence to support the claim? Well, notice if the p-value is less than alpha, what that means is we reject the claim, and here's what we're rejecting: the null hypothesis, and it says there is no linear correlation. So therefore we have sufficient evidence to support the claim that there is. The claim will always be that there is a linear correlation between these two variables. Our other method for decision making involves the test statistic and the critical value. If the absolute value of R exceeds the critical value, we conclude, again, the same thing. There is sufficient evidence to support the claim of a linear correlation between X and Y, and we'll use the correct language for X and Y. So what we mean, if it exceeds the critical value. So it may be that our test statistic exceeds and falls in here, or it could possibly fall in here. Either one of these critical regions indicates that we reject the null hypothesis. So if neither one of these, if these aren't the case, of course these two should agree, it's just two methods to come to the same conclusion, but if our p-value is not less than alpha and our absolute value of R does not exceed the critical value, we conclude there is not sufficient evidence to support the claim of a linear correlation between X and Y. Okay, those are our choices for conclusions. Alright, so this is very much like the hypothesis test we've done before. I didn't write my last statement here, but I would have conclusion, and we would write that sentence, a nice sentence summarizing our conclusion. Okay, if we conclude that there's a linear correlation between X and Y, we can find an equation that best expresses Y in terms of X. You know, if we have a linear correlation, we're saying our data pretty much follows a line, and lines have equations, right? So that we'll be able to come up with an equation to represent that relationship. And that equation can be used to predict values for Y for given values of X. So we'll discuss this further in the section on regression. The predicted values of Y will not necessarily be the exact result. We'll use this equation to predict, but it won't be exact because there are other variables besides X that are affecting Y, such as just random variation or variables not included in the study. So like in my example of the plants, there are other reasons why a plant might grow besides sunlight. It could be, you know, just the type of seed. Perhaps there wasn't great control over the different types of seeds that they used, you know, from different sources, or perhaps a different amount of fertilizer in each one, or there's just many reasons why perhaps one plant would grow a certain height. So there are other variables. Certainly sunlight will have an effect. It's a variable that will have an effect on plant height. We would expect that. But there are other variables that would also have an effect on plant height. So we know that it won't be an exact prediction when we use this regression equation to predict, but it'll be, if we've determined that there's a relationship, it'll be a useful prediction.